Okay, so first, like Benoit, I'd like to thank the organizers, especially Hamanaka-san, for organizing this event, which brings together people from both mathematics and physics. And of course, it's always nice to be back to Nagoya, where I spent a certain fraction of my life. So today I'm going to discuss part of this paper, which we put out in February to the archive. And this was in collaboration with Faru Musabian and Yahao Zhou. However, I noticed that I should probably start on some background material. And so this story is a lot of exciting story for me in the sense that it seems to expand the narrative in somewhat unconventional series, and which is why I'm excited about. On the other hand, of course, the flip side of the coin is that here in this story, I don't claim to understand everything. In fact, it raises more questions than answers to some extent. But I feel that at least I have the correct picture to incorporate everything. But it doesn't mean that I worked out everything, but that's the nature of the story. So rather than jumping onto this, I probably start with some somewhat more broader perspective. And fortunately, I have two lectures, so I might try to cover somewhat more introductory material, which is actually interesting in its own, and it brings together a lot of the research questions. But that's the lecture one, and then lecture two, I come to a little bit more into this direction of discussing this model. But before coming to any details, let me start with some basic outline. And this research is motivated by the following two observations. The first observation is what I'm going to explain mostly in the rest of my first lecture. So it refers to a class of series, which also appeared on the web page of this conference, and a class of series related with each other. In fact, I'm going to write the four corners. In the rest of my talk, I might make the picture gradually make the picture more and more complicated. So with a lot of more series, but at least one of the basic ingredients is this six-dimensional theory. Six-dimensional theory, which is a holomorphic version of the Chern-Simons theory. Holomorphic Chern-Simons theory. So hopefully people can see it. So please let me know if you can read it. And so this is a holomorphic version of the Chern-Simons theory. And then the other corner is that you start with the four-dimensional version of topological holomorphic topological. You can call it HT Chern-Simons theory. So Benoit was explaining a hierarchy of theories, and this is in the middle. And so there is a relation between the two. And on the other side, there is, well, you can call it like the four-dimensional Wess-Zumino-Witten model, which is related to the famous equation, this anti-self-dual Yang-Mills equation. So this is the nice set of equations, and then classical equation motion for that of this series, the anti-self-dual Yang-Mills equation. And so this is the other side of this story. Now, what's nice about this is that it seems to connect a different type of integrability in the story. So fortunately, Benoit was explaining some version of this. So if you have a topological holomorphic theory, in my notation, I'm going to write this on sigma times c, where c is the same notation as the previous lecture, where c is the holomorphic direction. Holomorphic direction, and then there's a statement is that you get two-dimensional integrable quantum field theory. Let me write this IFT, integrable field theory. Well, I'm going to get in general, I'm going to get a quantum field theory. Although in this lecture, I will not discuss too much of the quantum aspect. Although that will, some version of the quantum aspect is extremely crucial for discussing that. But the actual thing I'm going to discuss are mostly classical. And you can imagine that the quantization gives rise to that preserves the structure. Now, an integrable field theory with the Lux connection, as discussed in the previous lecture. And so this is the diamond of a series. So we have a 60 series. So in the end, at the bottom, you have a two-dimensional integral field theory. And well, of course, depends on the construction, we get a different integrable field theory. But let's say the prototypical example for that discussion in my lecture is a two-dimensional Wissam-Witten model as an example of the theory. And so it's not actually not too surprising that you have a four-dimensional version of the Wissam-Witten model, and then that reduces to two-dimensional version. And here I have a reduction of this to the integral field theory. So this is a diamond series, and it brings together, well, it raises a lot of different questions. So you can try to generalize these constructions and things like that. And then what happens to here, or like, can you translate this into that? That is the first setup. So, and well, and then this, from in a viewpoint, if you think about it, some of the ingredients are already there when people were discussing the twistor theory for this equation. And but let's see, at least the connection to this type of the story is somewhat new. And in the case, this raises, you look at this picture, it raises a lot of questions. So that's the ingredient one. Now, completely separate from that, at least on the surface, there is a different statement in the literature. And that's a statement about the relation between this generalized Katz model and the hyperbolic monopoles. So this is the observation going back more than 30 years ago by Atiyah. And also Atiyah Mari. More than 30 years ago, in the early 90s, 91 and 95, if I remember correctly. And this makes of the following observation. So, so let's see. So there is some integrable model called a generalized. Sorry. In fact, in his discussion, he wasn't talking about the generalized Chiral-Potts model, but he was talking about the Chiral-Potts model. And I'm going to explain a little bit more what this model is, but this is some integrable model. Okay, integral model in what sense? Well, it's a solution of the Yang-Baxter equation. Now, this Chiral-Potts model has a curve, which is like that holomorphic curve C. So this one has a spectral curve. So people studied this interesting model, Chiral-Potts model, which is a very peculiar one, as I'm going to explain. And then in particular, whatever model it is, it has a spectral parameter, and the curve associated with it, it's a spectral curve. And now the observation he made is that this spectral curve has something to do with spectral curve or something completely different. Of monopoles. Monopoles on the three-dimensional hyperbolic space. So I'm going to call it a hyperbolic monopole. And again, this is a separate ingredient. Well, let's see, with the gauge group SU2. And then, so what Atiyah observed is that if you compare these two curves, they look very similar. Now, the precise correspondence between the two is a little bit subtle. And I'm going to explain a little bit more hopefully. But these two curves are very similar. Well, there is a little bit more ingredient. There is this parameter n, and if you take a quotient by Zn, then And then if you take a special parameter, this goes to that. What is n? Well, so the chiral Potts model is a spin model with, so it's a lattice model. So for each point on the vertex on the lattice, there is a parameter, which is called spins, takes values in Zn. So for example, recall that, for example, this contains, the chiral Potts model contains as a special case, the Ising model. The Ising model is, hopefully you know that the Ising model, there is a Z2 spin, plus minus at each vertices, and sum over that. And this is, well, of course, there is a generalization of that called the Potts model, which you might be more familiar. But that's not the only generalization of the Ising model, and that's the chiral Potts model. But the spin variable is the same as the Potts model case, and it still takes value Zn. So that gives one integer, n, which runs from 2 to 2, 3, 4, etc. Now, on the other side of this monopole, well, again, I'm not going to explain all the details because I'm coming to that hopefully afterwards. But at least the monopole has a charge. Monopole charge. And suppose that you have a monopole charge n. And then this n is translated to this n. And then one curve, and then take a Zn quotient, you get this curve. So that's what you observed. Well, to make the statement a little bit more precise, there is more parameters, and somehow you have to eliminate the parameters by going to a special configuration of monopoles to match this. There is a monopole moduli, for example, but this is more rigid. But at least setting aside the details, here just made observation. Just take this one. I mean, forget about all the context where it comes. So just stare at the curve, and then take a quotient, and it's the same as the curve, which is again another curve. So that's the observation Atiyah made. And interestingly, almost nobody, as far as I know, literally close to nobody followed up on this observation. Probably close to zero, despite more than 30 years. And probably there is a reason for that, which is that this observation is rather mysterious. So nobody understood why this is the case. No explanation whatsoever. And so this was another ingredient which I want to incorporate. Now, a priori, I mean, these two have nothing to do with each other, a priori. However, there are some indications that these two might be related. So this is the monopole. Well, it's a hyperbolic space, and I'm going to make that a little bit more precise, but at least the monopoles. And the monopole is a solution of the Bogomolny equation. It turns out that that's a dimensional reduction of the anti-self-Yamez equation. So there are a nice set of equations, and then there are not too many nice set of equations. And anti-self-Yamez is like the godfather of everything. And so the hope, by looking at this, you might hope that maybe there is a way to connect these two. So namely, this is an anti-self-Yamez equation in 4 dimensions, and you can go to 3 dimensions. 3-dimensional equation known as the Bogomolny equations. I can write Bogomolny, but let's try monopole equations. So this is an instanton, if you like. Well, in the usual case, we consider R3. We have to go to H3. We have to think about it. But before setting that aside the details, at least it's well known that the instanton reduces the monopole. There's ADHM constructions, and there's a non-pole, and there's the T-duality extending between the two. So that's how. So the monopole is at least something which is closely related to this side of the story. Now, what about the chiral Potts model? Well, I haven't explained anything about the chiral Potts model, but at least it's an integrable lattice model, solutions to the Yang-Baxter equation. Now it turns out that this four-dimensional topological holomorphic Chern-Simons theory, that is a theory which is also excellent at explaining integrable lattice models. So here in this picture, I said that I reduce it to here, and you get the quantum field theory. And that's the that's the story which appeared in the one-dimensional lower version of that appeared in the previous talk. And that's what I did with Kevin Costello. But this is not the only type of the story. So in fact, you can also do a slightly different thing. And then go to two-dimensional integrable lattice model. So this is the content of originally due to Costello and then Costello and myself and Ed Witten. So this is a slightly different story. So what's the difference is that on this side of the story, I'm going to incorporate the one-dimensional defect. So obviously, if you have a one-dimensional, it breaks the translation invariant. But if this one-dimensional defect makes a lattice, it makes an integrable lattice model. So that's the story. Now, on this side, you have a two-dimensional. On this side, you have a two-dimensional defect, so that you get the quantum field theory. So that's the discussion. If you like, there is also a relation between these two, which is discussed in my paper with me, Ashkumi Kumar, and Junichi Sakamoto, who is sitting there. So, but let's see. So that's the important thing is that here you can start with the topological homomorphic Chern-Simons theory. And then what we observed is that you can actually realize a lot of interesting quantum integrable lattice models. So here you have a solution of the Yang-Baxter equation. And then we got a sad news that C and Yang passed away recently, and also Rodney Baxter a few months ago. So so that's so we are in a new era of the integrability kind of. But let's see. The solution of the Yang-Baxter equation is another characterization of integral models, and then the Chiral-Potts model is on this side. It's an unconventional side. And so far, nobody actually derived the full expression from this perspective, but at least on this side. But that raises the question. So then the question is that, sorry, this is getting messy, but the Chiral-Potts model, I might write a CPM as a Chiral-Potts model. So the Chiral-Potts model is on this side. So this raises the question. Maybe these two are not unrelated. So what Attila observed was pure observation, not really no geometry or no art. Just compare the curve. The curve is there, but he wasn't explaining why it comes. But looking at this, there is a hope that maybe the monopole, you start from here, you go there, go to 60 Chern-Simons. Well, in our paper, we actually go to 10-dimensional Chern-Simons to take care of some signature. But I'm not going into this. 60 is more or less enough. Let's go to 60 Chern-Simons, go down, and here, and you get the Chiral-Potts model. And maybe that explains this structure. And in which case, the fact that you have the same curve might be explained by the fact that you have some single curve here, which go down here, which go down there. Of course, there's a little subtlety. You have to take a quotient and everything, so you have to take care of that. But the hope is that the question we are going to address and answer partly at least is that so Atiyah Mari so the question is that can you explain Atiyah Mari in the 60 perspective? That's the question. And of course, it involves several different questions. For example, as a smaller question, for example, Atiyah's observation was restricted to gauge group SU2. But if this type of explanation holds, it's natural to extend the correspondence to other gauge groups. Well, of course, there could be extra subtleties, but this is a homomorphic Chern-Simons with gauge group G, for example. You can do that for any gauge group G. And as far as we see, there is no reason why this should be SU2, for example. So, and then that involves the Atiyah Mari for SU2. So that, sorry, SUN, SUN. And then in this lecture, I'm going to use SU small n. So this small n is different from this large n. So it's a little bit confusing because there are two different n's. This n is the number of spins or monopole charge, whereas SUN, this is a small n, so AN minus 1. For example, this is one of the questions we should address. And also other things. For example, so Chiral-Potts model. And then also related question is that Chiral-Potts model, that this really arises from four-dimensional Chern-Simons theory. So this involves questions like this. And in our paper, we discussed some of these ingredients. Now, let's see. For example, for this case, for this thing, so it involves so this will raise a lot of questions like this as a kind of like a corollary. But in practice, we're going to address each by one to make this solidify this story. Now, for example, I can comment a little bit briefly on this thing. So what about gauge group SU small n? Now, of course, it's easy to guess on one side. On one side, it's extremely clear. So this should be SU small n. Now, it's just a spectral curve monopole for gauge groups SU small n. It's very natural. Now, then there should be a counterpart of this. And it turns out that there is some generalization of the Chiral-Potts model. There is no canonical name, but I'm calling it a generalized Chiral-Potts model. So this is the model discussed by Bajanov, Sergeyev, Mangazev, and Kashayev, I guess. And then it turns out that if you do this, you increase the number of components of spin to SUN, capital N to the power small n minus 1. So for n equal 2, this power is just 1, so you just have a Zn spin. But in general, you have a copy of the Zn spin. So that's the structure you find. And of course, that's the type of thing you might expect. Usually, SU2, it's complicated group, but if you know the representation theory, it's made by combining SU2, kind of. And the simple roots, there are many simple roots, but the number of simple roots is small n minus 1. And this has a similar flavor. For example, our paper involves several ingredients. For example, we generalize this correspondence first to SU small n. And then check that first, that you can do, just take the curve, compare, and whether it gives the same data. And then once you have that, you can ask a question of how to incorporate this into the whole story. And so the goal of my lecture is to some extent, first to explain, as I said, some basic picture, even before going to this more complicated story, like of how does the general story of going back and forth between different series work. And then afterwards, I try to come to a little bit more specific into how this could work. Any questions so far?
Naive question.
Yes.
Is there any duality exchanging capital N and small n?
That's a very interesting question. And yeah. Let's see. Well, in fact, there is a known connection of Chiral-Potts model to so that's a two-dimensional integrable lattice. But then there is a connection to the tetrahedral equation, Zamolodchikov. And then in that discussion, I think that was this model, I think. So in that discussion, you have for example, you have a two-dimensional lattice and then stack the two-dimensional lattice with a small n copy, for example. And then you get the series of tetrahedral equation. And it looks like a three-dimensional. And in that picture, you can flip. And then this you can exchange the role of the two. There was also a related statement about so it's a level representation theory. It looks like a level rank duality kind of, and there was a discussion that
you mean we should consider three-dimensional integrable system?
Yes, so, yes. If you start with the three-dimensional, sorry, let's see. First of all, if you just take a Chiral-Potts, there was a statement that if you can consider a stack of well. It's actually not exactly this, but at least if you consider Chiral-Potts model, make a stack. stack of that. And then you can interpret as a three-dimensional lattice model, satisfying the tetrahedral equation. And then you can exchange the two. So that is a known statement, which is closely related to your comment. Now, that's the pure statement about chiral pods. And how it's related to this is not too clear. It's a similar idea, but this small n is like SUN, so it's kind of like a stacking, but not exactly, right? So SU3 is not copies of SU2, etc. So I think it's not exactly that, but if there is a way to connect to that discussion, I think that will answer your question.
Okay, thank you very much.
Any other questions? Okay, so if not, let's try to start a little bit from which corner. Yeah, let's start from four-dimensional Chern-Simons. Somehow that's the theory I'm more familiar with. Yeah, so let's say four-dimensional Chern-Simons theory. So we see a very closely related version of that in 3 dimensions, a mixed BF theory. This theory is also very similar to that. So let's see. Well, so this is defined on the manifold of time sigma times C, and the C is holomorphic. For the purposes of my talk, the C you can think of P1, CP1, possibly with some punctures. And now on this CP1, so I can consider the omega, which is a holomorphic one form dz over z. The simplest possibility. And of course, this has a pole at z equal to 0, but also at z equal to infinity. So you can write this as there are two special points, 0 and infinity. Or you can write it in a different coordinate, like a cylinder, 0 and infinity. So that's the holomorphic curve. And then you can write down the action, omega, which Chern-Simons 3 form, where this is the usual Chern-Simons 3 form, the AHDA plus and then this is integrable over the 4 manifold. And some of the comments which appeared in the last lecture applies. So this has a z component already. So the z component of the gauge field doesn't matter. So you can forget about that component. So A has the, so let me write the coordinate of here as WW bar. This is Z bar. And so the gauge field component has AW and AW bar, and AZ bar, but no AZ has components. But of course, it's still a field in 4 dimensions. It depends on all the 4 coordinates. Now, there is a statement that, well, it gives rise to integrable field theory. And the argument is very similar to what appeared before. So the equation of motion of this theory, so this is really a z component. Equation of motion of this theory says that, well, in fact, if you like, you can also take a coordinate, go to a local coordinate and go to ZZ locally. But let's see, if you go to that coordinate, equation of motion says that this is really a flat connection, wedge omega wedge f equal to 0. So you can think of it as a C with the infinity removed, infinity and 0 removed. So, and this equation says that, so this is, so this equation says, first, and then let's see, of course, this equation says if ZW equals to if Z bar W equal to 0, if W bar equal to 0. So these are the 3 components. Now, if you go to a gauge where AZ bar is equal to 0, this gives rise to the condition that this is 0. And then, of course, this is still the relation. Well, if you like, Okay, I don't even need to write it, but let's say if you just write down explicitly. Now, this equation means that AW bar are holomorphic in Z. So a priori, it depends on both on Z and Z bar, but there is no Z bar dependence because the derivative is 0. So I can write AW Z. As far as the Z dependence is concerned, it depends only on Z, but not in Z bar. And it satisfies this flat connection equation. So this too means that if you define the L, so this is defined on sigma plane, WW bar, AW. So this depends on WW bar, but also Z, DW plus AW bar, WW bar, Z, DW bar. So this is a one form on the WW bar direction, which is the sigma. And this one is flat. So L is lux. And we encountered almost the same discussion towards the end of previous lecture. So we have the equation of motion of this thing, and then it means that something is flat automatically. Now this Z, just like the previous lecture, Z from the two-dimensional viewpoint, Z is often called the auxiliary parameter, extra parameter whose meaning was not clear, but now it's part of the four-dimensional geometry. So it's something you can. It's already there as an input. So if you use the flatness existence of flat connection as an integrability, then it's known to be you get the integrable theory somewhat automatically. Now, of course, precisely which theory you get depending on ingredients, and you have to incorporate the defects. Again, just like our previous talk, you can try to incorporate the defects. And depending on what type of defects you include, you get the different the theory. Now, since I want to explain the connection to this Witten model, I can actually consider the simplest possibility, which is really this. Nothing else. So that's well, I'm doing physics, so it's always nice to start with something simplest. And so what about in this setup? What is the theory you get? Or this theory? And it turns out the answer is something many of you already know, actually, if you studied the Chern-Simons theory. So what two-dimensional field theory you get from this? Now, the way to think about it is to look at this cylinder. Now, if you have a cylinder, there is an extra S1. And if you have an extra S1, you're doing string theory and all that. It's often natural to compactify along the circle. So indeed, if you have a 4D Chern-Simons theory on sigma times the cylinder, maybe I should write the dotted line. Okay, somehow I don't like this. Maybe I like this. Anyway, so if you have a cylinder, then you can think about dimensional reducing this along the S1. And what you expect is that you should get the three-dimensional Chern-Simons theory. And that is not too surprising. So you have the dz over z. So now in this coordinate, dz of z becomes just d of something. So dz tilde, if you like. And of course, what you do is just do the Fourier decomposition along this S1 and take a constant mode, or in physics it's often called the zero mode. If you start with the 4D Chern-Simons, and omega is just the d of some coordinate, and you just do take the zero mode, you just get the usual Chern-Simons because that part is gone. So this is this is a dimensional reduction. Well, you can also go back and forth if you like. And so taking the zero mode is a version of the T-duality in the field theory, if you like, which people discussed in the context of supersymmetric field theory. In fact, you can also start from here, make infinite copies, and go back. But anyway, you get a 3D Chern-Simons theory, which is a very simple theory. And then on the interval, sigma times interval. And this is the precise situation where we have a canonical quantization of the theory. And then here, in particular, there are some boundary conditions. Importantly, there are some boundary conditions here and there. And then there are important boundary conditions which you can discuss. So 3D Chern-Simons, still, initially we only have 3 components, so it really becomes a 3 component. So Z bar, it was complex here, but it becomes I can keep calling it Z bar, but Z bar becomes one of the real coordinates here. But let me keep using the same notation. AW bar, AZ bar, for example. Now there are 3 components, and then you have to put the appropriate boundary conditions. And then there are multiple different boundary conditions. But the most typical one in the Chern-Simons discussion, which is the same thing as discussed in the original paper of Schwimmer, Seiberg, and Kutasov, I guess, is that you put the holomorphic boundary condition. So you put either, say, holomorphic boundary condition. On the other side, you put the anti-holomorphic boundary condition. I think you're going to put this as well, if you like. So there is a complex structure here on W and W bar, and then you put the holomorphic anti-holomorphic boundary condition there. And then this becomes the somewhat familiar setup. So you have a 3D Chern-Simons theory with the boundary condition. Here it's a holomorphic. This is anti-holomorphic. And then this gives die2. So this gun gives I2, two-dimensional with the Witten model. But this is really a two-dimensional CFT, which involves both chiral and anti-chiral block. But this chiral anti-chiral decomposition is a general feature of a conformal field theory. But here it has a nice geometrical inclination. So there is a chiral part coming from here, an anti-chiral part coming from here, maybe the other way around, depending on the convention. So you have a chiral plus anti-chiral. So that's how you get the two-dimensional Witten model in this case. So it turns out that in this particular case, you just reproduce something people discussed. If you like, this is the Baruch boundary correspondence, Baruch H correspondence, but the point is that, of course, if you go to 4D Chern-Simons, you can include multiple defects and etc. to obtain some generalization of that. But for the purposes of two-dimensional Witten model, you can actually go through this route. Now, if you want to go directly starting from 4D to 2D, what you should do is, of course, here it's the defined on sigma. Of course, you should eliminate this C. The C is CP1. So you have to integrate out the field along this C direction. To get this Witten model. So you solve the equation of motion along C, and then that of course depends on this coordinate. So if you plug in the solution to the action, and then that we get something which depends on all these directions. And the statement is that gives like to two-dimensional Witten model. So that's one of the ingredients so that's part of this. There was a big diamond, and this is just one of the lines of the diamond. Yeah, so indeed, this was one of the corners of the diamond, and this is one of the other corners of the diamond. Now, probably I spent a little bit too much time. I'm going too slow, but let's see. But then once you understand this, you can imagine going to higher dimensions. So let's try to go to higher dimensions. So instead of starting from 4-dimensional Chern-Simons theory, let's try to start from 60 Chern-Simons theory. Well, there are some subtleties I'm going to come back to, but what about 60 Chern-Simons theory? So this is often called the holomorphic Chern-Simons theory. This is a cousin of the 4D Chern-Simons theory. And in fact, action leads very similar form. So this is a 6D geometry. And then omega times Chern-Simons 3 form for some gauge field A. Well, I might write it a calligraphic A to just give you a feeling. Now, so this is a 6D geometry. And this is now, we need a 3 form. Previously, we just have a 1 form there. But we need a 3 form. In general, you would need a global 3 form, which requires a Calabi-Yau, and I'm coming back to the subtlety how to go beyond that. But let's say this is the action, and then this is a holomorphic 3 form. And then just like this before, the AZ components is absent. So here you have AZ1. So there is no Z1, Z2, Z3 components, and only the anti-holomorphic connection. So this has a 0-1 connection. So if you like, A is sum over AZI 1, 2, 3. So there is a holomorphic or anti-holomorphic connection. So 0-1 connection. And then, so in fact, there is a natural relation to the 4D Chern-Simons, not surprisingly. So you have a 3D Chern-Simons with a dimensional reduction of 4D Chern-Simons. So of course, in general, depends on the geometry. But for example, if this is a R4, for example, times 2 torus, you can go to this, take a T-dualized to go here, for example. So it's they are all related. But this one, of course, is 1 dimension, 2 dimensions higher. So it's a more powerful theory to some extent, more constrained. Now, if you start with this theory, you can make so one of the diamond is indeed going to 4 dimensions. So that's where then I can come back to the diamond. 4D Chern-Simons on. So this is on sigma times C, but P1 with some puncture. What I described so far is that this goes to 2D WW. And this is the reduction along P1. And this is defined on sigma. Now, suppose that I have a 60 Chern-Simons. And suppose that I have let's say I call it E, like you can call it as a torus if you like. And then you can have a on sigma times yet another E. So we can think about the torus. In some contexts, I'm going to replace by flat R2. But these are essentially flat space for my discussion. Now, you can also try to imitate what happens here when you first compactify on P1. So what's going to be the result? Now, well, of course, you can try to repeat the same thing. So here, I start with 4D Chern-Simons and get the 2-dimensional Witten model. And then what's the theory we get? The theory we get is the 4-dimensional version of the Witten model. And the relation between the two is very similar. So here you have a 1 form omega wedge some form, but that's replaced by holomorphic 3 form sitting in front. And here the relation is also similar. You have an action, 2D action, and wedge that to the 2 form to get the 2 form, which is the Kera form here. So you get the Kera form wedge, whatever action, That's the definition of the Western-Witten model. So this relation, this part is T-duality equivalent. So this is defined on sigma times E. Now, this for this WW has something to do with, at least if you write on the classical equation of motion, you get the anti-self-Yamil's equation. In fact, people became interested in that in the study of the anti-self-Yamil's, as far as I know. And hence this is the this completes the diamond. Now, well, of course, you can try to look at this and try to extract things a little bit more, or try to reinterpret things. So here you have, so for example, the lesson here is that if you reduce along the P1, it looks like this. And then there is a flat connection equation, which is the equation of motion that becomes a Lux equation here. Now, the lesson is that it looks like an innocuous equation of motion, but on this side, it looks like a Lux equation, which is hard to find. Well, actually, in the case of WCW, it's not that hard to find it. But in general, you get the Lux equation, which is hard to find because you don't see this spectral curve P1 as a part of the geometry. You have to guess it. The beauty is that you go here, you can make it somewhat more systematic. Now, you can try to repeat the lesson here. So you have the anti-self-Yamil's equation. Of course, it's a well-defined equation, but a priori, it's not completely clear whether there is any Lux type structure or any integrable type structure. And the lesson is somewhat similar. You have this extra P1. So there is something nice about it. So there is this extra P1, which emerges this story if you start from 6 dimensions. And indeed, if you look at the literature of anti-self-Yamil's, I'm not too much an expert, but you find the P1s popping up in the twistorial construction. So so the point is mapped to, I think, P1, yes, in the twistor space. So this is actually like a twistor P1. So if you want to study this, it's actually useful to go up there because some information is there. And in fact, so let's say, so here I have taken to be a little bit more general. So, but to make the correspondence to the twistor a little bit more explicit, I can come back to the question of what is this theory. So this action is actually highly constrained because we need to have a globally defined holomorphic 3-form omega. And then that says that in one definition, it's a Calabi-Yau 3. So if it's a Calabi-Yau 3, this is well defined. And you can write on the action. And because of that, people have limited options. Requires Calabi-Yau 3. Now, one option is to take CP/3/4, for example, which is what was used in the twistor string, for example. Okay, I wasn't writing C, so maybe P3/4. So 4. So this is a twist. So people did a twistor theory associated with this super projective space, which is relevant for the study of equal force, super scattering amplitude, and all that. So there's a beautiful story. But instead, we can also try to do something different. We can actually try to start with the P3. We can try to do P3, but of course, P3 is not Calabi-Yau. And the way out is to allow some singularities. So let's see. Okay, this is a little bit, or remove the P1. So on the P3, there is no globally defined 1 form, so 3 form. So if you try to find something, it has some singularities. But that means that if you start with P3 and you remove something, then it effectively, on the complement, it looks like a globally defined 3 form. And then you can discuss the geometry. So you can discuss P3 and with point taken by P1. Now, it turns out that this P3 So is a twistor space for twistor, I think for S4. So this is R4, 1 point with together with infinity. 1 point compactation of R4. And then this P1, taking this P1 is like removing the line at removing the point at infinity. So each point is mapped to one of the P1s, and you remove the point the line corresponding to infinity of this R4, so that you get R4. So this is the I think you can call it as a twistor for R4 if you like, and then you get that ingredient. So it turns out that in fact the correspondence with the twistor works pretty well. So here I have this geometry. So you can the sigma itself, sigma we can take to be very general, but here I can take. I mean, sigma itself doesn't play too much role here in this discussion, so I can make it to be R2 or T2 or some. So let's say R2, and then it turns out that this P3 and P1 taken to. So this is the twistor geometry for R4. And this is as a smooth manifold. It's O1 plus O1 over P1, and in this fiber direction. So it's a fiber direction. You can think of this as you can take to be sigma and E, which if you take it to be flat R2 or flat geometry. So. And then hence you get you actually get this on P3 minus P1, P3 with the P1 of the infinity taken out. So indeed, not just the twistor line, but the twistor space is also appearing here. So so that's what was discussed. Well, so it's in a sense a reincarnation of the twistor philosophy. That was made most explicit by a paper by Kevin Costello, and then Whittlestone and Skinner followed up on that. So that's this line, which is like if you like, I explained this story but through conventional Chern-Simons with Witten correspondence, it's some sort of like uplift of that, and you cover many of the stories of the twistor space. So that's how the story goes. And so that's the explanation of how the diamond works. Any questions at this point? Okay, if not, I seem to have a little bit like 7 minutes. So let me try to start gradually making a segue into the next topic, which is about trying to understand the generalized Katz model, generalized Chiral-Potts model in this context. But now I have a limited time, so rather than introducing the generalized Chiral-Potts model, which is on this side, let me make a brief remark about how to connect this. So this is the instanton. How to dimension reduce to monopoles in hyperbolic space. So that's yet another ingredient. So there is a well-known connection between 4D instanton, sorry, not 4D Chern-Simons, I'm doing too much Chern-Simons. 4D instanton on R4. And then we replace that one of this direction by S1. And then this reduces to 3D monopole on R3. So it's an instanton, and so it's regular point-like, and it's still a point-like, and it becomes a monopole. Of course, this relation is non-trivial, and especially, yeah, so it's related to how, for example, people discuss fractional instantons or social confinement, and it has a lot to do with the difference between these two. So, but in any case, at least the relation that 3D monopole you can regard as instantons. You can construct the instanton solutions up there. And then if you like, you can impose the S1 reduction. You can look for solutions which is S1 invariant, and then that reduces to the 3D monopole. So that's how the correspondence works. Now, of course, people try to generalize the monopole solutions to other manifold. And then it turns out one of the nice solutions, well, typically, okay, I forgot exactly how, but typically you're interested in, maybe that was a requirement. It's useful to consider constant curvature manifold. And then the other possibility is, of course, the hyperbolic space. So this is like, just make sure, so this is like, so, okay, maybe I write on the metric, if you forgot what this is. So this is like, what coordinate? Yeah, r squared plus dx squared plus dy squared r squared in the upper half plane model. So in the upper half plane, and then you put in the coordinate. So this is r, and this is xy direction. So this is the hyperbolic 3D hyperbolic space. And it turns out, well, let's see. Well, naively, it doesn't have, so I want to have something like a H3 times S1. And then I can do this. Now, you might worry that H3 times S1 is very different from R4. But it turns out that R4 is actually conformally invariant, sorry, conformally equivalent to H3 times S1. So the anti-self-Yamazaki equation, there is no scale, so it's conformal as a classical equation. So it actually does, it's the same as this. But to make the correspondence statement a little bit more precise, I actually have to write R4 with the R2 taken out. So that's the statement, and that's the same as the H3 times S1. So you have to take out something. So we saw something similar, H3, and you have to take out P1. And so even downstairs, we expect something similar. And in fact, we are seeing something similar. So we have geometry, but some things are taken out. Now, this is not difficult to see because R4, so you can write down ds squared. So I can take a radial coordinate in two of the directions. Well, of course, this breaks the covariance, but it's OK. I'm not going to preserve it. So I just wrote down two of the directions and then introduce the radial coordinate for that. Now, you can write this as, so you can do the conformal transformation, or you can just, OK, dr squared plus, OK, so this is a very trivial manipulations. So I just extracted r squared. So up to this conformal factor, which is r squared, this is the metric on H3. And this is the part of S1. So this is how the correspondence works. So if you take R4 and you do the conformal transformation, then it's actually H3. So that's a little bit different from what people do, but it's actually true. So this is one way to study monopoles in hyperbolic space. It's not perfect. If you do this, there is some quantization condition which is automatically imposed, which is not necessary, et cetera, et cetera. But yeah. So OK, maybe I didn't write down the monopole. Monopole is this equation, d phi, where this takes values on the joint. So this is the original equation, is if equals star f. Maybe minus, depending on the convention. So that's the equation. Now, it seems that I have 1 minute, so I can make one more remark. So what they said is that you can do the S1 reduction, and you get the monopole. Of course, you can keep track of what happens to the twistor construction. Now, OK, so it turns out that the twistor space here is the mini twistor space. So mini twistor space, it turns out that is the P1 times P1. Well, it's actually, you have to take the diagonal, take out the diagonal. But this P1 times P1, you can think of it starting with P3. And by quotient by C star action. So here, you are dividing by the S1. But in the twistor space, the interesting fact is everything is complex. So when you divide it by that S1 action, it promoted to C star action. Now here, so you have to take out the two lines, two copies of P1s, and then take some quotient. And that's known as the mini twistor space. And this is the action, so this involves 4 coordinates. And this acts by multiplying the first 2 coordinates. And you can work out that if there are 2 fixed points, fixed lines, and that's this. So this is supposed to be the twistor space for the H3. So that's the one geometric, one explanation coming from the reduction. Or you can take a different viewpoint. So what is a twistor space? Well, of course, I didn't explain what actually the twistor story works because it takes some time to explain. But at least I can quote one fact. So if you, for example, in the typical Minkowski spacetime, the twistor, in order to extract a point in the twistor space, you consider the null geodesic. And here we do something similar. So here we have H3, and then the boundary of that is a sphere, which is located at infinity. And so this is S2. Well, it looks like R2, but there is a point at infinity. So it's compactified, S2. And then you have to consider geodesic on this H3, which is, of course, people studied. And that's like the semicircle, semi or circle, yes. So this is the geodesic. This is a geodesic. And it's a geodesic. So once you start, all the trajectory is determined. Except that you have to choose the points. Well, so you can also take this, etc. But there are different choices. And the choices are specified by 2 points here. And then so let's call that Z and in conventional W bar. So once you specify 2 points on the boundary, you can specify there is a unique geodesic connecting these two. And it turns out that this P1 times 2 copies of P1s correspond to these 2 choices. So this Z and W bar, if you like. So that's why this twistor space arises. Now, in this discussion, so it makes a little bit unclear. So actually the twistor space, so the mini twistor space is actually, so let's see, sorry, I'm not, okay. The actual mini twistor space is essentially this, but with one more modification, which is that P1 times P1, and then take out the diagonal. So that's the point where, so if you take elements Z and W bar, where Z equal to W bar. That's the point where this geodesic collapses. So we take that out. And this is the mini twistor space. I might call the Z of H3. So this is the mini twistor space for this H3. And then so for the time is up, so let me finish. But what's important is that I started explaining how this twistor space arises, how the hyperbolic monopole arises from this deduction of the anti-safety Yamez equation, and then the mini twistor space is essentially P1 times P1. Well, you have to take out the diagonal, etc., but just a P1 times P1. Well, I didn't say too explicitly, but of course you have to fix the gauge group, and it turns out this is the case for SU2. But let's see. So if you go to SUN, there is a little bit of complicated structure, but effectively you have a copies of P1 times P1 patched together. So that's the one side of the correspondence. So we have some P1 times P1. Of course, this is just a twistor space, and then you have to solve the equation of motion, which gives that a line band on that on the spectrum on the twistor correspondence, and then that's going to be mapped to match with the Chiral-Potts model size. So in the next lecture, I'm going to explain first, remind you about this curve itself, and then also I introduce the curve on the generalized Chiral-Potts model side, which is from here, and then try to see the match and outline how these things fit together in this larger framework, which is the holomorphic Chern-Simons theory. Thank you.
Yeah, so let me start the second lecture. So, well, first, maybe let me remind you what I wanted to do. So there was a conjecture by Atiyah and Mari about the spectral curve curve of generalized Carrier-Potts model. So let's just go generalized Carrier-Potts model. So this is the SUN version. So general Carrier-Potts model and the relation between spectral curve of hyperbolic monopole. And so that was the relation between the two is the well, in fact, the Atiyah-Murray case was n equal 2. So that's the original Carrier-Potts model, and then I'm stating it for the generalized version. So and then so this is SU2 case, and SUN case is our work. And so generalized Carrier-Potts model. So this is a component. Spin is the n minus 1 spin. So it's a statistical mechanical model with spin taking values in this. So again, we have this capital N and small n. Just to remind you. And on this side, the gauge group is SU small n. So an minus 1. And a monopole charge with the monopole charge. So this is broken to the Cartan, which is U1 to n minus 1. So we consider the maximal breaking. So the monopole breaks the gauge symmetry to some subgroup. And I'm here assuming that it breaks to the Cartan. It breaks out to the minimal possibility. And then for each element of this U1, there is associated charge, monopole charge. And I'm going to denote the monopole charge. So there are small n minus 1 Cartans, and then there are corresponding monopole charges. And I take the monopole charges to be all n. Small n minus 1. Well, perhaps I should remind you that the monopole equations. So the monopoles are described. Poles are described by this equation: F equals star phi. Phi is the Higgs field taking values in the joint, and then it has some charges. So the charge. So this has what I might call the monopole charge. So this is the value of the first Chern class, or you can measure the charge at infinity. Okay, so maybe I can write as a measure charge at infinity. So fundamental weight of the F. So star F. So this takes values upon some appropriate normalization 2π or so. This takes values in integer. And then this I runs from 1 to n minus 1. And so these are the charges, which I denoted here. In general, the charges are different depending on the different charges. But here I consider the case, it's the charges are all the same. And there is also another parameter called the mass, sometimes in the monopole. Well, mass in the sense of the Higgs mechanism. And then that's the value of phi at infinity. So this is a scalar field taking values in the joint. And then you can talk about the asymptotic value at infinity. And this is all known as a mass of the monopole. And this is extra parameter of the theory. But actually, I'm going to take the limit where this goes to, so sometimes denoted by pi. And then unfortunately, there is no corresponding parameter on this general Carrier-Potts model side. So what I should do is to send this parameter to 0. So Atiyah did that already for the case of SU2. So it's a slightly generalized version of that. Now, well, of course, if you're a physicist, you might be a little bothered by sending this to 0 because this is a dimension full parameter. It has a dimensional mass. So, well, of course, you can set the mass to 0. But if you want a more invariant way, you can make a dimensionless combination. So this is a hyperbolic space. So H3, and H3 has a non-trivial curvature. So it's more like this one times the R of H3, the size of H3, the curvature, well, inverse curvature goes to go to 0. So the typical scale of the H3 is also going to 0, if you like. So you can trade between the two, I believe. Anyway, so if you don't mind that, you just eliminate this mass parameter from the description, and then the charges, you have to specialize to this particular one. And then everything is determined by this capital N and small n. And that goes to this generalized Chiral-Potts model. So the Chiral-Potts model itself was discussed, well, originally discussed not necessarily as an integrable model, but it was recognized that it's an integrable model in a series of papers, first by Barry McCoy and collaborators, and then there is another paper by Baxter, Heleon Yang, and Jack Park. So that's the SU2 case. And a generalization to SU small n case is due to Bajanov, Mangazev, Stroganov, Kashaev. And then the statement is that these two are related. Well, I'm going to make it a little bit more precise later. But to make a statement a little bit more precise, I'm going to take a quotient by some action with small n minus 1. I will be more specific how this acts, what is this curve and how this acts. But this is just a preview. And then these two curves are essentially the same. Well, there is a little bit of a caveat. There is actually modulus in this curve. The Chiral-Potts model has a curve, but it has a modulus. So you have to specialize the modulus to match this, for example. And also here it's if you want a monopole, you need some reality condition because monopoles are in the end real. But here there is no counterpart. You have to specialize, etc. So the correspondence is still a little bit subtle. It's not necessary that they're on the nodes the same on the nodes. You have to impose some condition to match. But you find more or less the same condition, same geometric structure, and that's what I'm coming to. Now, so let me try to, so the goal of my lecture today is to explain this correspondence in somewhat more detail, and of course, try to see how this fit into the larger picture, that how all these things are originating, or can be unified in the 6D description of the 6D Chern-Simons theory. So in the paper, we actually discussed the 10-dimensional Chern-Simons theory. You can go there. But I'm not really going to be too careful with the issue of the signature. So for my purposes, the 6D Chern-Simons is enough. Now, towards the end of my last lecture, I started explaining about the hyperbolic monopole, and then how, in particular, there was a mini twistor space, which is the ingredient for the description of monopole in the twistor correspondence. And I explained that from the 4D instanton. So this is H3, and the R4 taken to R2. If you take out R2, this is equal to conformally equivalent to S1 times H3. So this is the S1 reduction, the viewpoint. And that was the viewpoint originally taken by Thier. And that's conceptually somewhat useful description. And I like that description for my intuitive understanding. However, this is a little bit of a technical point, but it turns out that for some practical discussions, I find it hard to just follow the Thier's description. There are some reasons for that. If you start from the 4D instanton, it actually happens that S is an integer. Partly because these things are unified, so because it comes from 4D, and you cannot make it generic value, for example. And also, Thier's description is intrinsically algebraic geometric, and nobody has, as far as I know, nobody has really tried to complete the discussion. So this was Atiyah was for SU2, and nobody has completed the discussion for SUN, as far as I know. And in practice, we use the description, which is more or less speaking the same, but slightly different, due to not Atiyah, Murray and Singer. So they have a more analytic description of the whole hyperbolic monopoles, and they also work out the story for SUN, which is relevant for me. And in this Murray Singer description, they start with some set of null geodesics. So this is a set of points x0, x1 to x3. Let's see. So here I take a light cone, future light cone, 0 and x0 positive. So this is the future null light cone, and so that's the definition of U. And then that's relevant here. So that's a future pointing light cone. And the reason this is relevant is that H3 is U divided by R plus. So this R plus acts by multiplying all the entries by the same number. And then you can set this is negative, but you can set it to -1, for example. So that's the and then that gives the H3. And in the Murray Singer description, they actually always starting with U, and they do the twistor correspondence for that. And then only afterwards take a quotient. Now, in the twistor correspondence, given this U, I'm going to consider, so this is the deduction I want to do, and they're going to do things in this U. And then there is a twistor space corresponding to U. So that's a set of null lines, which is inside U. Null geodesics inside U. And it turns out that this is given by element, ZW. So these are each complex numbers in P3, such that some combination. So in fact, C squared. So I might like it as ZB. Okay, so in the A dot, in the somewhat twistor notation. And then I have a condition that A B dot one is conjugated. A dot is positive. So each is so these are homogeneous coordinate, and you have two complex numbers times and two copies of two complex numbers, and there is some condition that there is some positivity. So this is similar to the P3, which is the usual twistor space, but one real condition. So in particular, it's not the holomorphic manifold. So it's there, but there is a counterpart of that called the CR structure. CR stands for Cauchy-Riemann, etc. But some analog of the complex structure. Now, what they do is to start with this U, and then do the Penrose-Word transform CU. So this is a set of elements, gamma x, where x is in U, gamma is this line geodesic, and this contains so this is an incidence relation. And so the idea of this twistor correspondence is that you start with some solutions. So solution of the Bogomolny equations here, and then pull back and push forward, or the other way around. So we are going to have some line bundle here, and then a holomorphic bundle, and then you go there. Now, what we actually want is this H3, which is by the R plus reduction, and then similarly, what we have here is the Z of H3, and this is the CH3. Similarly, the incidence relation, and you go through here. And then this is also a R plus reduction. So this R plus reduction acts by multiplying to the first two coordinates. So ZH3 is ZU over R plus, where this R plus acts by, if you have 4 coordinates, it acts on the first 2 coordinates only. And this is similar to the action of the C star, which, if I didn't forget yesterday, I introduced yesterday. And then it has the fixed lines. So I think I wrote previously in yesterday that I can consider C3, for example, C star, and then give that to P1 times P1. So that was the mini twistor space I introduced before. And this is like, here you have a C star action, but we have R plus action, which is essentially the same action. And then you get mini twistor space again. So this is P1 times P1 with the diagonal removed. And so that's how the Murray and Singer formulated this statement. It's a little bit of a technical point, but I was tempted to mention it partly because one of the reasons that the publication has been delayed for many years is there are some subtle aspects of this twistor correspondence which requires a separate analysis. And so far, yeah, the Murray Singer paper was extremely useful for that purpose. Well, partly because if you want to discuss the complete moduli space, of course, you want to study the solution of Bogomolny equations, but with a specific boundary condition at infinity. And how to incorporate that in glory detail was the technical difficulty. And in fact, precisely speaking, it's not completely obvious if the Atiyah description matches with the Murray Singer description in general. Well, even for the SU2 case, etc. So that's a little bit of subtlety. Maybe that might not be too relevant for most of you, but at least it's some subtlety. So, but the important thing is that their description, they have the SUN version spelled out. And then the important thing is that in the end you have P1 times P1 either way. And so what you should do is to consider the bundles on it. And it's just like a P1 times P1. So what you should do is to consider line bundle ON on here. So here, the bundle you should consider is O, say N plus, N minus. So this is like, if you like, it's a pullback. Well, if you like, I can write it a little bit more formally. So this is like a pullback of the ON plus bundle from one copy, and then and another copy, O minus N minus, where each of these comes from one copy of P1. P1 plus, say, this comes from P1 minus. So that's the bundle, and then you can try to go back to the Bogomolny equation. So that's the bundle. So, but the important thing is that so that's there is a curve. So there's a structure on this P1 times P1, and yeah. So I call it a bundle, but this is just a P1. So you can think of it as described by some polynomial equation. And that is this description of the monopole.
Excuse me.
Yes.
So as you mentioned, the ZU is not holomorphic.
Not homomorphic.
So when considering some correspondence, in which category you work?
Well, let's see. So there is something called a CR structure, which you can define, and then that's the language they use.
Mhm.
I think instead of saying there is something like a Delbar operator you can define. Delbar operator is Delbar operator is some object which sends map to 0 comma something to 0 comma something plus 1. There is some operator, and then it satisfies some Leibniz rules and square to 0. So that gives a definition of the CR structure.
I see.
And then there is a holomorphic function, for example, CR function, and then the CR bundles and everything defined from there. So that's the language you can use. I don't know how essential that is, but at least that's in the end the structure they use. Yes.
But Attia's approach is purely algebraic.
Yes, purely algebraic.
So then somehow CR studies and algebraic studies correspond.
Well, I would expect that in the end, there should be a way to formulate everything purely algebraically, I think. But as far as I see, I don't see it in the SUN description, partly because you have to talk about the boundary conditions, infinity, etc. And it's easier to say that Higgs field takes this value and gauge connection takes this, etc. And it becomes very analytic. And yeah, there in the end, what you get is that there's because SUN you have a frag variety, frag bundles, and then there is a structure, etc. So I think in the end things becomes algebraic, but at least I didn't find a paper discussing everything algebraically. So well, for the hyperbolic case, yeah, I mean, so there is of course, for the usual R3, there are a lot of papers, but hyperbolic case, there are less papers. And then hyperbolic and SUN, for example, together with the most general boundary condition, etc. And it's sufficiently, complicated. So nobody really starts to study it except this Mari single paper, which is actually reasonably recent, like 2010 or something. So it's a subject on its own, and it requires a lot of analysis. So if there are experts in twistor theory, etc., I'd happy if you can dig into this particular aspect. But,
Thank you very much.
Yes. Yeah. So okay. So this is the description of monopole, and I should start coming to the chiral pots before the drill starts. So the chiral pot side. So what about the chiral pot side? Well, first of all, the general chiral pots model. Chiral pots. So what is this model? Well, of course, you can write down the Boltzmann weight and the R matrices, and there is some expression, which is interesting, but I'm not going to write it down because I'm not really going to use it. And then the only thing essentially I'm going to use is the spectral curve. But maybe if you want to have some idea, so as I said, this has a spin, takes values in Zn to n-1. And somewhat relatedly, it's related to the representation theory of the affine quantum group, SL n at root of unity. So it's some, whatever it is, it's some quantum group type structure. And you can imagine that you consider irreducible representations and consider the interdefiner for that. There is some representation called the minimal cyclic representation, which, well, of course, this is a root of unity. The representation theory is very different. And you can consider the minimal representation, minimal cyclic representations, and then consider the interdefiner between them. And what's interesting is that at the root of unity, the representation theory is very subtle because there is a large center. And when you consider the interdefiner, you should impose the condition that the central elements should take the same value. And the central elements are highly nonlinear, and that's how you get a highly non-trivial spectral curve. Now, what is the spectral curve? Well, I'm going to write down the spectral curve, but at least the genus has an interesting formula, which is 2n-1, n-1, minus 1, minus plus 1, I guess, plus 1, if I remember correctly. Yeah. And that's and then that grows very, very fast. And then let's, for example, specialize n equal 2. So this genus is, I hope I'm getting it correct. So n squared n minus 1 plus 1. So and then this is like n equal for n equal 1. So the g equal n equal 1, g equals to 1. But for example, for n equal 2, genus is already 10. It grows very, very fast. And then the important thing is that this does not fit in the standard understanding. So the standard understanding is usually the genus is 0 or 1. The spectral curve is either C or C star or elliptic curve. So this is called the rational trigonometric elliptic integrable model. But this one is completely different, has a very high spectral curve. Now, I said usually, but what do you mean by usually? Well, of course, there is a way to quantify it. So the usually means that there is a classification by Verabin-Drinfeld classification. And I'm not going to state this itself, but at least some of the crucial ingredients is that R matrices. So some R matrix. So the R matrix is associated with the crossing of the lines, and there are some spectral parameters associated with it. Okay, I'm not going to give a proper explanation of the R matrix because otherwise I will run out of time. But R matrix is some function which depends on two spectral parameters, associated the crossing of the two lines, and then there depends on two spectral parameters. And this does not take the form that it depends only on the difference. So this is called a rapidity difference property. Sorry, let's see. So let's say, suppose that if this is satisfied, suppose that this is satisfied. So this is called a rapidity difference property. And then another important assumption is that this thing, well, which now depends only on the single parameter, has the form of starting with identity and then small corrections with respect to some parameter called h squared, h bar. So there is an expansion parameter h bar, and you can solve it somewhat recursively. So this is called a quasi-classical R matrix. So what the Verabin-Drinfeld discussed is that if you assume the difference property together with the quasi-classicality with a little bit of extra assumptions, then you can show that the genus is either 0 or 1. And so that was the result, and that's usually what happens. And in fact, there is some justification. Well, this is you can debate it, but typically we are interested in the quantum group at the generic value of Q or h bar. So you can, in particular, take h bar to 0. Here, this one is natural. It's related with the Lorentz invariance of the theory. So okay, so to properly explain that, I have to go back to the origin of this spectral parameter z. But the Lorentz symmetry typically means that it depends only on the difference. Well, another way of saying that is that this spectral parameter is actually, it's a point of the spectral curve. So the spectral curve is, I was denoting C yesterday, and there are 2 points Zi and Zj. But typically there is a symmetry diffeomorphism here. So it depends only on the difference between the two. So if you assume these two conditions, then genus is 0 or 1. And that is violated here. It started. So that's but in part, so that's violated. In fact, in the Chiral-Potts model, in the Chiral-Potts model case, this is not satisfied. So it depends on two spectral parameters separately, and it doesn't have this form because it's a root of unity. So it's a very peculiar model. Now, what is the spectral curve for this model? And that's very interesting. And in fact, you can go back to the old paper by Bajanov et al. And if you look at it, you begin to find some structures which is very similar to the twistor discussion. So spectral curve of generalized Chiral Potts model. So let's prepare some variables. Z1 plus, Z2 plus, sorry, Z1 minus, Z2 plus, Z2 minus, Zn plus, Zn minus. So these are homogeneous coordinates inside P to n minus 1. Well, if you take n equal 2 in particular, this is P3, which is already like a twistor space for the R4 or S4. And and then inside here, the curve, the spectral curve C, I mean like a C and N. So remember, this is labeled by Zn spin to n minus 1. So capital N and small n. And this is defined by a set of relations, Zi plus n, Zi minus n equals Kij, Zz plus n, Zz minus n, where this K is a 2 by 2 matrix. So it's an element of GL2C. Well, it's for all for I, O, and J. So for each I, J, N. So it's defined by the set of equations. Well, of course, we need a consistency between these conditions. Well, so first of all, that should be the condition on K. With the condition Kij equals to, well, first of all, Kii equals to identity matrix, 2 by 2 matrix. Kji is Kij inverse. Kjk equals to Kik for consistency. To make it make the structure more symmetric, yes. Obviously, these are needed, otherwise it doesn't make sense. And then, of course, if you look at this, in the end, the only non-trivial or independent constraints come from this, where I runs from 1 to n minus 1. So there are n minus 1 conditions imposed. So n minus 1 conditions and there are 2 equations. So that, and then you see that indeed this defines a curve. And so this is a curve. So this is a curve inside P2n minus 1. Now, to make it closer to the spectral curve of a monopole, first I'm going to do a quotient of this. There's a free group action. Well, because everything is to the power n. Everything to the power n. So you can take a free quotient by multiplying each of these by root of unity. So we can free group action by Zn to small n minus 1, where each Zi plus Zi minus goes to omega, say Ki, Zi plus, omega Ki, Zi minus. Well, of course, the overall one is already quotient because this is a projective space. So you don't consider the overall one. So that's okay. So that's the so that one is that's not the extra free action. But otherwise, you can so this omega n equals to 1. and then consider the quotient of this guy. So in fact, I'm going to call it a tilde because it's upstairs, and then define C and N to be the quotient of this by this action. So this is the group action which appeared like 30 minutes ago, but I'm now giving a more explicit description. So this is the spectral curve. And so you don't lose too much by going down because there's already a trivial group action. So that's the curve. And well, of course, that's still a curve inside this P2n minus 1. Now, I want to connect it to some curves inside P1 times P1. And we already saw that how to get that. For example, for n equal 2, it's P3. So that's like a twistor space for R4, S4. And then I took a quotient by C star to get the curve P1 times P1. So if you do that same thing for n equal 2, you actually do exactly that, and you get a curve inside P1 times P1. For small n greater than 2, you can still do the same thing. So in fact, there is a projection. So you have 2n minus 1, and you can try to reduce it to copies of P1. And copies of P1 by further quotienting. And hopefully the notation is clear. So for example, you have Z1. Okay, maybe I just, it's a little bit too much to write down. Okay, I can try to be explicit. Z1 minus, Z2 plus, Z2 minus. And then introduce the extra C star action. Lambda 1, Z1 plus, lambda 2, C star. This is 1. Lambda 2, Z2 plus, lambda 2, Z2 minus. Where these take values in C star. So you can take quotient by C star to n minus 1. And then you get copies of P1. And then each of the P1s, so each of the ith copies of P1. So this is labeled by Zi plus, Zi minus, labeled by each pair. Well, of course, you have to check that the equations defined there is compatible with this action. And you can check that if you multiply each of these by some C star, and then it can be compensated by the action of C on the here, etc. So it's an overall multiplication. So this quotient is consistent with these equations, and then you get a curve. So this defines a set of curves. C and N defines a curve inside the copies of P1. And now, once you have that, you can in particular take a copy, ith copy, for example, I plus 1 copy. So you can project into the I component, I plus 1 component, P1I, P1I plus 1. And then there is a curve inside it. I might write the CI, and it's inside here. And this is simply defined by the equation that Z plus Z minus is equal to KI plus 1, W plus W minus. Yeah. to the power, oh, okay, to the power n is already modded out because I'm downstairs. So there is this curve. Well, maybe I explained these things in an overly complicated way. What I'm doing is very simple: P2n minus 1, and then some equations, and you just quotient to go down to copies of P1, and then have have a collection of curves. So in the end, collection of curves. Ci inside P1 times P1. Yeah, so indeed, if you, yeah, so let's see. Sorry. Okay, so I think I should have the n here still. Yes. So I have a collection of curves inside P1 times P1. And that's essentially looks very similar to the spectral data of the monopole. So this is a mini twistor space. And then in that description, there was a curve inside it, which is a spectral curve. So that's more or less how ATIA noticed. In the case of ATIA, n equal to 2, so we just have P3 and then reduce it P1 times P1, and that's the same as the P1 times P1 spectral curve. Well, of course, in order to say the same, I have to specify what I mean by the same. So this Ci is, first of all, by degree, n comma n, because it's defined by n's polynomial equation. And then this is real. Real and I think compact. So it's a some curve, compact curve. And what else? And you also have to talk about, so if there's just a single curve, it's okay. But of course, we have a collection of curves. And we want to see something like a Dinky diagram structure. And then there is an extra condition. So I'm running out of space, so let me write it down here. Perhaps it's better to write here so that it's easier to see. I can continue here. So I can talk about the intersection between the two. So what is the intersection? Well, if you invoke the Bezout theorem, generically it has n squared, 2n squared points. And let's consider the generic setup. 2n squared points. So this is 2n squared points. But it's related with the real structure. You can actually see that, sorry. To match with the monopole, there is one more condition. So this splits into, well, they use this notation, Ci plus 1 over I. But what this means that there are n squared points. So there are 2n squared points can be decomposed into n squared points and n squared points. And then these are exchanged by the real structure. So that's what is needed to match the structure on the monopole side. And so this condition, well, unfortunately, if you take a general element of K, this is not satisfied. So if you take a general element of the Chiral-Potts model, and then that condition is not satisfied, so it doesn't correspond to any hyperbolic monopole, at least in the standard sense. But you can try to make sure that this is satisfied. And so this is if Ki inverse Ki plus 1 is elliptic. So this is an element of GL. Well, now I impose the reality condition. Well, sorry. First of all, this is real and compact. So for that, I need to impose the reality condition. And then essentially, well, these Ks are complex in general, but I have to make it real. So this is satisfied if Ki is element of GL2R, not 2C. Now, what about this condition? So this is satisfied if this as an element is elliptic or parabolic. In other words, not the other one. Sorry, not I forgot. Yeah, elliptic or parabolic. So elliptic parabolic means that elliptic means the trace is so in other words, trace of this guy. So if the trace of this guy is 2 or greater, 2 or smaller. So smaller elliptic is smaller, and it's 2. It's a parabolic. So that's a classification of the conjugacy class of SL2R matrices. So if you impose this condition is satisfied. And now it turns out that if you look at the description of the monopoles in the Murray-Singer, that's this type of description they find. In other words, you have a collection of curves inside P1 times P1, and each is by degree n comma n, and it's real because I want a real solution. And then, well, we have to see the Dinkin diagram type structure for SUN. And that's specified here. So you consider I plus 1 because it's connected by inside the Dinkin diagram. And then that's the condition. And you have to impose some condition on the K. But if you impose that, that's satisfied. So these data define so after these conditions, well, let's see. So let's see. Maybe we can here. So we can write here. We can match. So hyperbolic monopole data. So hyperbolic monopole data means the set of curves satisfying these conditions. Okay, so that's more or less how we match the data. Well, there is a little bit of subtlety which I'm hiding, but let me not come to that. But rather, I should try to come to the more fun part of how to incorporate this in the Chern-Simons theory. So far, I just explained how to match the monopole spectral curve data, spectral data of the two sides. And by hindsight, it's the fact that you have P1 times P1 on both sides more or less explains why there should be a match. Now, explanation from 40 Chern-Simons and the 60 Chern-Simons. And one of the inputs needed for that purpose is that you need to explain how to get 40 Chern-Simons, how to start from 40 Chern-Simons and the general Chiral-Potts model. Well, okay, so let me not talk about the general Chiral-Potts model, but the special case of Chiral-Potts model. So this is n equal 2 case for simplicity. That's needed for this discussion, and then that's a very subtle discussion. And in fact, that's partly related to the fact that in the description so far of the Chiral-Potts model, and sorry, of the integrable lattice model, we often do genus 0, 1. And this is not genus 0, 1, higher genus. But there is a way out. So the spectral curve I denoted by this, which is a very higher genus. But you can represent it as a branched covering over P1. So branch covering means that the map is not one-to-one. In general, there are many to one-to-many, and then there you can go around and then go to a different seat. There's so that is with a completely general theorem. You have a Riemann surface, and then you can represent it as a branch cover over P1. That's a very general theorem. So not specific about this case, But what's nice about this particular case is that it's described by some very concrete algebraic equations, as we have seen. So we can try to be a little bit more explicit in our description. And then the thing is that we can try to write down some one form here on P1, and then try to pull back to the one form on the spectral curve by using this projection. Now, I impose a little bit of an extra condition. For example, I impose the condition that this has no zero. And in fact, OK, so it's a little bit too much to explain that in detail. But for example, one of the reasons, for example, I said that people like the genus 0 and 1. And what is the reason? One of the reasons is that on the genus 0 and 1, you can write on the one form, which has no zeros. So if you go to a general Riemann surface, if you write on the one form, it also has a 0 due to Riemann-Roch theorem. But on the P1, for example, if you write on dz, this has a pole at infinity, but no 0. Such a thing exists only for genus 0 and 1. And that's related to the fact that you can write on some nice boundary condition, which is topological, and hence ensure that the resulting R matrix, which you can compute from 4D Chern-Simons, satisfy the Yang-Baxter equation. Now, I want to impose something similar to that. So I want to write down some expression which has no zeros. And then I want to impose the condition has no zero. And also, clearly in these discussions, we've seen powers of n, some variable to the power n. So if it's a generic nth branch cover, it can be more general polynomial. But here, there is a clear Zn invariance. So invariance up to the Zn action, which I introduced before. In other words, everything is already to the power n. That's the formula we encounter. And also, well, of course, there is some topological condition. Because, of course, you already know the genus of this. So there is a Hurwitz formula, which says that, which determines the genus of this, given the position, how many branch points there are, and also at the branched degree for each of the branch points. So if you determine the branch structure, and the genus upstairs is determined. And that genus should match the genus here. So that's gives the structure of what type of branch cuts there are. And it turns out that the answer we wrote down, so that there's not necessarily a unique answer, but we wrote down a minimal answer, which takes this form, z to power n minus z sum 1, z to power n minus z2. Well, of course, if you write this, it's nice that it has only the power n appears. So it's a Zn invariant. But it's still singular. And it turns out that we proposed to write down this formula with the nth root of this expression. And indeed, if you count the degree, this one doesn't have any 0, for example. So that's our proposal. So this is the spectral curve. And then in the Chern-Simons description of the integrable model, that's part of the geometry. And of course, if you like, you can keep doing that. And that's the description, most natural description. But if you like, you can also use this description downstairs. And in that description, there is some advantage. It becomes something more familiar P1. But with this structure, in particular, it has a branch cuts. So the remark is that so in addition to this, reproduce the correct genus. of this spectral curve. And also explains why absence of difference property. So the difference property I introduced 30 minutes ago is this thing. So this Zi and Zj doesn't take the form that it depends only on the difference. And usually in the Chern-Simons theory, as I told you, there is a translational invariance. So that's why you expect this. There is a translational invariance of the series, so you should be able to do this. That's the intuition. But here, it's not. And then the explanation is that there is a branch cut. So when you try to discuss this, you have to be very careful which seat you are. And you are at, and that explains the absence of the difference property. And then this one also has a nice one nice property, which satisfies the form that if you take a z bar derivative, it's equal to 0. Well, of course, this is like a funny manipulation. But let's say, so for example, this if you take a derivative, for example, okay, this arises. In fact, this also arose in yesterday lecture. And then why does this matter? Well, it matters in the discussion of the Chern-Simons theory. So in the action of the Chern-Simons theory, you have A wedge dA. And then take a variation of this. So you can take a variation of this. And then, for example, there is a term like this becomes del A. And then integrate by parts. If you integrate by parts, you get something like a del bar. Trace A wedge del A. And if this is non-zero, there is a new contribution. So you have to worry about that. But it turns out that this is a relatively low power. So if you do the manipulations, there is a delta function you get, but there is some power of z at that point, which vanishes, and because of that, there is no such contributions. So that's one property. So the statement is that if you take this one form, and then you can realize the Chiral-Potts model, it remains to be seen how or whether that's actually the case. But that's the statement. So let's see. Perhaps I should remind you that. So the statement now is that I start. Well, perhaps I should try to finish by writing this down again. So here you have a 4D Chern-Simons, and then on the spectral curve. So you can take a description of C star, or P1 with the branch points, or P1 with branch point. And then you can get generalized Chiral-Potts model. So it's almost like the curve itself is there, but instead you regard it as a P1, because in the previous discussion, what we had here was a P1, not this homogeneous curve. But the proposal is that you have a P1, but you choose new defect, which gives that to the branch structure. So the branch points look like a defect. And you can try to go up and down, and then not everything is worked out. But in the end, you get 4D. So in my description, anti-self-dual Yang-Mills, and then do the reduction 3D monopole, hyperbolic monopole. And then that explains, in the end, why there was a relation between the two. So that's the narrative. Now, the time is up, but let me, for example, comment on what are the questions raised by this. But there are obviously a lot of questions. For example, so here I have a proposal for specific curve and a specific one form and a specific setup where you might get a Chiral-Potts model. But of course, Chiral-Potts model is a very specific model with an explicit expression for the R matrix and Boltzmann weight and everything. So one obvious question is whether we can reproduce that. Now, it's associated with the root of unity. So in the Chern-Simons language, it's very non-perturbative. So it's not necessarily easy, but you can think about it. Now, you can also try to get inspired by this and look for generalization on either side. For example, here, previously, I considered the case where the monopole charge is ON, which is somewhat symmetric with this with the wide group action. But you can consider the case where all these integers are different. So monopole with a different charge. And then it's natural to imagine that it could be some integrable model with that. And that's not known. But if you compute the genus, suppose if you have well, I can try to use exactly the same logic and compute the genus of this tentative model. And I get the formula like ni squared and sum of ni minus 1 plus 1, I guess. You have some formula like that. So if you, well, of course, it's not completely obvious if this argument guarantees that there is a corresponding model. But if you take this correspondence seriously, and then for these patterns, there should be corresponding integral model whose spectral curve lives on the spectral whose spectral parameter lives on the spectral curve of this particular genus. So that's a prediction, if you like. And then there are many some generalization like that. You can discuss SO, SP, or E-type groups. And then on the monopole side, it's complicated, but essentially for all D groups, if you know the SU2 monopole, you can try to embed the monopole into SUN structure. That's how you construct the monopole. So you can discuss other gauge groups, for example, which should be related to the representation theory of affine D algebras of other types at the root of unity. And then also we can, for example, here we consider the breaking pattern of SUN into the Carl term, but maybe it's into the, it might not be completely broken. SU3 broken to SU2 times U1, for example, the breaking pattern. What is the meaning of that? And also here I sent the mass to 0 to match this description, but what is the, and so there are a lot of questions you can ask if you take this correspondence seriously. And to some extent, answering that is partly, it was interesting partly because it may extend the integral models, and or it may make the understanding of the monopoles better, but partly because that will be ultimate consistent check of this unified story. And hopefully, this is not, in a sense, this is a particular setup where the correspondence between the integrable lattice model side and if you like, the twistor side of the story. But hopefully, we can extract much more general lessons out of that. And that's very much in line with the themes of this workshop. Thank you.
Thank you for the very nice and interesting talk. And is there some question or comment?
I'm not familiar with the hyperbolic monopole. Is there any deep brain interpretation of the monopole?
Well, let's see. Not too explicitly. So I don't think I didn't find a literature discussing that explicitly. So, however, I mean, some of the things I can say because, yeah, at least in the reduction, well, of course, one way is to start with the R4 and R2, and then do the reduction, that gives rise to H3. And you can try to imitate that. So, namely, you start with the D4, D0 standard description, and then put in the defect, which feels, I don't know, some brains in splitting the two directions out of 4. So it's, yeah, D0, D3, and then maybe, yeah, some brains, it should be supersymmetric, I have to think. Some dim brains fitting that. And then if you do the reduction along S1 here, which is like a T-duality along that direction, then you get the setup for H3. So that will generate that. But of course, the one good check of that is there like a non construction type description? Because if there's indeed such a brain construction, and then you can analyze the BPS condition, they derive the NAM construction. So that was one of the advantages of this. And then you can ask, but then it's a relevant question is there nice NAM construction for this hyperbolic monopole? And there, I noticed some papers, but not in too much detail. There's something called a discrete NUM transform, which seems to be relevant for the hyperbolic monopole, but not too much discussed. And also, to what extent people have proven that the NUM data matches the hyperbolic monopole, especially for SUN. That seems to be a little bit obscure, and certainly not the definite result seems to be known. I know a couple of papers, but yes, so that's the state of the art. So I would say, in fact, even at the level of on the monopole side, NUM data is not worked out. And then you can also try to work out deep brain realizations. So it seems to be widely open.
Okay, thank you very much.
Thank you for the presentation. Are there any other known correspondences such as this one?
Yeah, the answer is no, and that's makes things surprising to some extent from this viewpoint. I mean, it's related to the fact that the general Chiral-Potts model is essentially the only model with a very high genus spectral curve. Well, there's some other model which is proposed, which I'm not sure if experts agree, and but that one is a completely different construction. So this is essentially the only model ever with a higher genus spectral curve. And people, of course, people in the integral model got excited already back then, and then keep trying to search for that for the past 30 years or so. But this is essentially the only model. But if you take this correspondence seriously, then this side seems to be more flexible. I mean, it's a little bit more constrained. There is a reality condition or some condition here, etc. So in that sense, it's a little bit more constrained. But setup-wise, it seems much more general, right? So, I mean, here I also have a reduction to H3, but here on this side, there are various different reductions you can do. You can do reduction to, I don't know, KDB or like a lot of different things here, for example. And then what are these, for example? That's completely unknown.